shared structure and shared parameters comes up in directed models, but it comes up as much or perhaps even more in undirected models. And that is because, for reasons that we've already discussed and will continue to discuss, eliciting parameters in an undirected model is much more difficult because they don't represent conditional probabilities or probabilities. And so it's a lot easier to represent them as sort of templates that are comprised of smaller building blocks. So let's talk about log linear models and why and how we might share parameters in log linear models. And it turns out to be quite easy once you think about life in terms of log linear models. So let's go to one of the simplest examples that we've discussed, which is that of Ising models. So Ising models, as you recall, is a model that was first invented in the context of statistical physics, where we have a bunch of binary random variables, each which in this case, in the original application, represent the spin of atoms in a certain grid. So here's a spin going one way, and here's a spin going, the pink one is a spin going in the opposite direction. And we have correlations between the spins of the electrons in adjacent atoms. And what we had as our energy model in an Ising model is a sum over all of the edges in the Ising model. So in this example, the edges are organized in a grid of the weight that represents the connection of the spin of the two adjacent atoms times this feature over here, so f of xi, xj, which is the product of xi and xj. And just as a reminder, xi are all either -1 or +1. So the product is always either -1 or +1, -1 if the two have different spin, and +1 if they have the same spin. Now, this doesn't have any shared parameters because we have a separate parameter wij for every pair of atoms I and j. But clearly, we're not going to have, in general, a separate model for every number of atoms in the material that we're trying to model. So usually, what's going to happen is that we're going to just have a single parameter w that represents the interconnectivity between, or the extent of the influence, extent and type of the influence of two adjacent atoms on each other. And so this is now a model that has the same feature and the same weight. So same feature and same weight reused across different pairs of random variables in the model. Okay. In the natural language processing example that we have used previously, so we have again a parameter sharing where we have, in this case, these are just as a reminder, we have these being the actual words, these being the labels for the words. This is the named entity recognition problem, but the same thing happens in other examples. So here we have, we talked previously about the kinds of features that relate, for example, a label of a word and the word itself. For example, if it's capitalized, it's more likely to be a person. If the previous word is Mrs., it's more likely to be a person too. And so here again, we have features, which are the ones that we just talked about. Feature of, for example, is yi a person and xi is capitalized? And we would have a term that uses this feature repeated for every position in the sequence. That is the same feature which talks about the connection between the label of the word and the word itself would recur in every position in the sequence, because you wouldn't want that same to represent a different parameterization for different positions in the sequence. And similarly, we have the same energy terms, for example, that relate adjacent words also being repeated across different pairs, in this case of adjacent words. Image segmentation. In this example, once again, we have node potentials that represent, in this case, the connection between the image features and the label. And once again, we're going to use the exact same potentials for all pixels. And we're going to have a different, in this case, set of potentials that are going to be reused for all adjacent pairs of pixels or superpixels. So how do we do this? It turns out to be really simple. What we basically need to specify for a given feature that we want to reuse, we're going to specify for it a set of scopes. That is the set of scopes to which we would like it to be applied. And so if we have a set of scopes, and let's assume that dk is one of the scopes to which we would like to apply the feature k. So our energy function now is going to include a term wk fk of dk in the energy function. So for example, if fk is, we want to have fk be applied to adjacent superpixels in the image. So the scopes of a feature fk will be the label yi, yj, such that I, j are adjacent. And that's going to be the set of scopes to which we apply that feature. And every time that we have that feature applied, we're going to have a term that multiplies in the value of that feature times the weight, which is shared. The weight depends on the feature, so wk depends on k, but not on the scope. So this is just a way of replicating the feature with its weight across different subsets of random variables in the image or in the model. So said otherwise, and I wrote all over this, so let's see if I can erase this. Yes. We will have a term in the energy function which has wk times the sum of the features across all the scopes to which it applies, which is just a way of aggregating like terms that all have wk in them. So to summarize, in log linear models, it's very common to use the exact same feature and weight for multiple subsets of variables. We've given multiple examples of that. And this allows us, just as in the other examples that we've seen in the directed case, to provide a single template for multiple Markov networks, whether it's the Markov network for different images or for different sentences. And the parameter and the structure are then reused both within and across Markov networks. And the only thing we need to do in order to apply this is to specify a set of scopes to which a particular feature is going to be applied.